Welcome to the R&D Lab. This is where great new innovative ideas are brought to life. The equipment we have in this lab allows us to create solutions and also to test and validate those solutions. This is the Surface Mount Technology Reflow Testing Area. Surface Mount Technology, or SMT as it is more commonly known, is used for creating the printed circuit boards that go into all electronic devices. The method for attaching components to the PCB uses a screen printer to place solder paste on the areas where you want the components to be attached. The component is then placed on this bed of paste and the whole board is placed in a reflow oven. Commercial reflow ovens look a lot like long pizza ovens, and the boards travel through the oven, melting the solder as it goes through the different zones. Once the board then exits the reflow oven, it cools down, the solder solidifies, and you then have an electrical and mechanical joint for each component. In the PEM product range, we also have fasteners that have been designed to provide mechanical threads on PCBs. These parts have been designed to be reflow soldered to the PCB in exactly the same way as the other electronic components. This SMT oven here, though not as big as a commercial reflow oven, allows us to mimic the reflow curves specified by our customers and also by solder paste manufacturers. We use the same solder paste, the same screen printing technique, so we can get exactly the same result as our customers do. The installed parts that we then have put into the test PCBs can be tested for their mechanical performance, both for the push-out and for the torque-out. In addition, custom parts can be designed and tested to ensure that they meet the required performance levels. XRF. The next station is the XRF. This is a very useful piece of kit, as it allows the measurement of metal thicknesses of platings and also concentrations in solutions. In addition, it can also provide a spectrum analysis of unknown materials, which from time to time can be very useful. The XRF works by using a focused X-ray beam to raise the energy levels of the electrons in the outer shell of the metal atoms. When these energy levels then decay, they emit the excess energy at a specific frequency and amplitude, and by using some clever calculation, the amount and identity of the metallic element can be established. In this way, we can figure out what metal is on the part, even though we already know what that should be. On the next bench, we have two pieces of test equipment. First one is the 4-wire low-level ohmmeter. This enables the ultra-accurate measurement of the electrical resistance of a joint. This is very important when designing fasteners suitable for current-carrying applications, and also for high current busbar applications. One of the most important aspects of an electrical joint is its overall electrical resistance. This equipment allows that value to be determined very accurately. Next to it is an 80 amp DC source for testing the current carrying capability and therefore the temperature rise of the electrical conductors. This allows us to create derating curves for electrical fastener products. In turn, these curves allow electrical designers to select a correctly rated product for their application and environment. Tensile tester. This is a tensile tester, which is rated for 5 kilonewtons. Whilst this is a smaller tester than you normally get, it is designed for greater resolution and enables very accurate testing of microparts performance. We also have larger tensile testers for the standard size parts. However, this tester is sized for testing the micro product range. The PEM micro product range packs a large performance into a small outline package. It has found great success in consumer electronics like phones and tablets, but also in automotive cameras, radars, and lidars. This tester allows us to demonstrate the incredible performance of the micro part, particularly when compared to a much larger standard screw. It also allows us to design parts with better performance. 3D printer. This is our 3D printer. It is capable of printing practically any shape and in a variety of materials. Equipped with a dual print head, it can choose from a selection of 6 reels loaded in the machine. This has enabled a much faster development cycle in the R&D process. Ingress protection. The final piece of equipment in this area are for ingress protection calculation. The IP67 chambers and the helium leak tester. The IP67 rating says that the joint can withstand a depth of 1 meter of water for 30 minutes without visible water ingress. This is a go, no-go test, and while it is useful to know how the fasteners perform against the IP standard, we need more resolution when designing better and more high-performing fasteners. The helium machine here can detect helium at very low concentrations. By configuring our installed fasteners with a helium source at one side of the joint and the helium leak detector at the other side, we can determine what the helium leak rate is through the joint. This enables us to determine an IP, i.e. ingress protection rating, for our installed fasteners at a very accurate level. When making changes to the design, we can tell immediately if we have a better joint or not with this type of testing. Since helium can get through even the smallest of the leaks, which water can't, you will always get a reading from the helium. Technical Cleanliness Lab. Here we have our Technical Cleanliness Lab. This lab is where we analyze our parts to determine their level of technical cleanliness. The standard for cleanliness in the automotive world was established by the German auto manufacturers back in the 1980s when fuel injection and ABS braking was developed. Cleanliness was very important for the components of these systems, as any stray dirt could cause a problem with their function. Hence, they created VDA 19. This cleanliness standard was then adopted for ISO 16232, which became the international standard for technical cleanliness. Both standards are essentially the same. So, to determine the cleanliness of components that customers would experience, you take a sample of the finished parts, preferably from the final packaged product in the warehouse. These parts are then placed in the particle extraction machine here in the lab. A specific amount of washing fluid is then sprayed on the parts for a specific period of time. This washes any loose particles free from the components, and it drains out of the bowl at the bottom through a filter at the side of the machine. This filter is then removed from the machine and placed in a vacuum drying chamber. This removes all of the cleaning fluid, leaving the particle contamination behind on the filter paper. The dried filter paper can then be weighed to determine the amount of dirt in the sample, or, as is more common, it is placed under the microscope to count the number of particles in the sample. The filter paper sits under the microscope on an XY movable table. Under computer control, the filter paper is divided into a grid of 16 by 16 locations. Each location is moved under the microscope in turn, and a high-resolution photograph is taken. These photos are then stitched together to give an overall single high-res picture of the filter paper. Each photo, as it is taken, is analysed, and the particles on the paper are measured and counted. The whole grid analysis is then repeated, but this time using polarized light, which allows differentiation between metallic and non-metallic particles. Fibers are identified by their length versus their width. Finally, all of this data is then collated into a report which is stored in our database and can be furnished to customers internally and externally. The report can be written based on the cleanliness standard specified, be it VDA 19 or ISO 16232, or, as we sometimes see, a customer-specific standard.